Good morning! On to the next lesson, predicting hidden behavior using f prime and f double prime. Okay, 4.3. We're going to be in this section probably until the end of this week. Okay, and just remember, what the heck is hidden behavior? Well, hidden behavior is just finding maxes and mins, whether the function's increasing or decreasing, the concavity, meaning whether it's concave up, concave down, points of inflection, doing all these hidden behaviors, finding these things basically without a graph, okay? And the next part we're going to look at here is the first derivative test, okay? That tests for local extreme values, and it's not just local, it can also be absolute, okay? Doesn't have to be local extreme values. It could be absolutes, which that was a really bad place to put that. So that really could be local or absolute, okay? And by doing that, okay, we're going to look at, or by finding those extreme values, the first thing we need to do is we need to find our critical points at x equals c. Well, okay, we can do that, and we know that we find that by finding when the first derivative equals 0 or when the first derivative does not exist. And also think of that as first derivative does not exist if it's undefined. So you can think of that as does not exist or undefined. And bottom line, when we do our number line test for the first derivative test, if f prime changes from positive to negative at x equals c, then we know f has a local maximum. Because essentially, what that means is if the first derivative changes from positive to negative, what that means is f changes from increasing to decreasing, meaning we have a maximum value there at x equals c. And also, this is just kind of a secondary point, f of c has to exist in order to be a maximum or a minimum, okay? Because if that maximum, or if x equals c happens to be a whole, okay, well, I don't have one there. So f of c has to exist, and there has to be a change from increasing to decreasing. If that happens, there is a maximum. Okay, I don't know if it's an absolute maximum or a local maximum unless I compare it to the other maxes and mins in the graph, but I do know it's going to be there, okay? And same way, if f prime changes from negative to positive at x equals c, well, then it has a local minimum, meaning if it changes from negative to positive, that means the original function f changes from decreasing to increasing, hence creating a minimum value at x equals c. And again, f of c must exist for that extreme value to happen, okay? And number 3, if f prime does not change signs at x equals c, then f has no local extreme value at c. And remember, when I'm looking at these critical points, okay, I can have flattenings in a graph that are not extreme values. So the derivative can equal 0 with a flattening. That's a really bad one there, but it's a flattening. So I have a flattening there, but it's not a maximum or a minimum, but it is a horizontal tangent, okay? Just remember that can happen. So we're going to look at endpoints here quick, okay? Maximums and minimums, and this is by definition at a left endpoint x equals a. Okay, so if f prime is negative for x being greater than a, then f has a local maximum at x equals a. What the heck does that mean? That means if I have an x value of a here, and I come to here and I'm like, okay, this is f of a, so here's my left endpoint. And what that means is if f prime is negative, what's happening is if f prime is negative, then my function is decreasing, meaning that is a local maximum value. And I don't know if it's a local, it could be an absolute at that endpoint. I don't know unless I compare it to all of the other ones at the same time, okay? And then in the red down here, that just means over here, if I have my a value and I have my f of a value here, and if this is my left endpoint, however, the first derivative is positive, well, that means my function must be increasing in some way. That makes this a local minimum value, okay? And that's all that means. That's how I'm kind of testing my left endpoint. And when I'm testing my right endpoint, okay, so we are looking at the derivative to see if the function's going up or down to say if it's a max or a min. Remember, endpoints are always going to be extreme values. So at the right endpoint, well, if I have an a value here and I have an f of a value here, so I have this right endpoint. Now I know to the left of that endpoint, if f prime is negative, well, if f prime is negative to the left of that, well, that means the function's decreasing to that point, making that a local minimum. Okay? So if f prime is decreasing to that point, well, then it's a minimum. Conversely, if I have this a value here and this f of a value here, and here's my right endpoint, well, if the derivative is positive to the left of that as it's approaching that, well, that means the function's increasing to that point, making it a local maximum. And again, I don't know if that's a local max or an absolute max, and I would only know, how to classify it local or absolute when I compare it globally to the graph over the entire interval we're talking about. Bottom line, if my right endpoint is at a and the derivative as I approach that right endpoint is negative from the left, means function's decreasing here, well, then it's a minimum. And if it's positive, it's a maximum because my function's going to be increasing to that point, meaning that's going to be a high point, okay? So that's really what we're kind of looking at for my maxes and mins off of endpoints, and in the middle we check for decreasing and increasing on both sides of our critical values. But please remember, when we're finding extreme values and we have a closed interval, you have to consider the endpoints on the right and left side as long as it's a closed interval, all right? So we're going to move on here, and here we're going to predict concavity. And I'm not going to fill in this whole portion yet, because this gets a little funky in your mind sometimes, at least it does for me. And we're going to predict the concavity on the interval from A to B, okay? So what we do kind of think about is we know if f prime is less than 0, well, we know f is decreasing, right? So if we're thinking of the second derivative, if the second derivative is negative, well, wouldn't that mean f prime has to be decreasing? And I say it has to be decreasing because the second derivative was basically derived from the first derivative, okay? So if the first derivative is decreasing, if I'm looking at the graph of the first derivative and it's decreasing, well, then the second derivative is going to be less than 0, and that's comparing it all the way back to the original function. And f, I'm going to leave this out for the time being, and that's going to give me my concavity. Well, also, if f prime is positive, well, then we know f is increasing, right? Well, how do we know that? Well, here's my original function f, and f prime is derived from f, okay? So if it's increasing, I have positive tangents, right? Well, how about if f double prime is positive? Well, doesn't that mean then the graph or the function from which it came from, f prime, was also increasing? And I'm not saying f prime is greater than 0, okay? I'm just saying f prime is increasing, meaning it's going up, okay? From left to right, it's going up. I can increase at a decreasing rate, and I can increase at an increasing rate, and that's talking about concavity. But if f double prime is positive, okay, the function from which this was derived must have been increasing, and it came from the first derivative, and hopefully that makes a little bit of sense to you, okay? And I'm going to fill that line in a minute. So we're going to, I don't know if you have to flip your page or not, but what I'm thinking about here, I'm going to think this is going to be my graph. I don't even have to write graph. I'm going to say this is my original function f of x, okay? And I'm going to make a graph of f of x. And I don't want it to be flat there, but this is f of x, okay? And what I can see here is I can see f in this case is always increasing, okay? And because it's always increasing, therefore, f prime of x, okay, that is always going to be greater than 0 because it's increasing, right? I'm going to have positive tangent lines. Well, what does that mean for concavity? Well, if the function's increasing, well, what I want to think about this is I want to look at tangent lines for a second, okay? So I'm going to come here, I'm going to grab blue. And the derivative, okay, I want to see f prime is always increasing because I can kind of see what's going on here. And when I'm thinking of concavity, okay, how do I want to say this? I want to back this up a second. I want to get rid of all of those, and I want to leave f is always increasing, therefore f prime is always greater than 0, all right? Now, what I want to look at is notice f prime is always greater than 0. However, f prime is decreasing. When I split this in half, what I need you to see is I kind of cut this down the middle. That's not an asymptote. That's just cutting my graph in half. When I look over here, I'm kind of looking at f prime, and f prime is decreasing here, okay? And on this side, f prime is increasing. And the reason I say that is I'm looking at the tangent lines, okay? So what's happening? Yes, all my tangent lines, okay, I'm really steep there, and I'm getting less steep. Now notice the first derivative, the slope of all these tangents are always positive, but notice my tangent lines are getting lesser in value. Their slope is getting less, meaning the derivative is actually decreasing here, okay? So this is increasing at a decreasing rate. And then when I get over to the other side where f prime, where the function, where I'm less, and then as I go, my tangent lines get steeper, well, f prime is increasing there, right? So what does that mean? Well, I can kind of see over here to the left of this, how do I want to say this? This side's concave down, and this side is concave up, right? So when f prime is actually decreasing, okay, f double prime is going to be less than 0 or concave down. And when f prime is increasing, meaning my tangents, as I go left to right, my tangents are getting steeper, okay, f double prime is greater than 0, meaning I'm concave up, okay, concave up. And this side, concave down. So I can think about that. Well, that's just like off of a cubic function. And to make sense out of this a little bit further, let's kind of look at a parabola here. That's kind of a crappy parabola, but I'm going to see if I can move. Oh, I can. Try to get him so his vertex is a little bit better there. Okay. Okay, so when I'm looking at my parabola over here on the right side, that cute little pink bugger, that's f of x. That's my original function. Now, I want to split this guy in half just to see what's going on both sides of it. So obviously, when I'm looking at it, f is decreasing on this side, correct? Which means the value of the derivative is going to be less than 0 at all those points where f is decreasing. Okay, on the right side over here, I can see f is now increasing, okay, which means the value of my derivative at all these points on the right side of this thing are greater than 0, meaning the derivative would be positive. All right? Now, what I want to do is I want to look and say, well, if f prime is less than 0, okay, over here, so all these values, all these tangent lines over here, okay, that just means they're all negative. But as I'm moving left to right, what do I notice about those? I can kind of see actually what's happening here is f prime is actually increasing in value as it goes from left to right, because I'm going from a very negative slope to a less negative slope. Hey, that's increasing. And if f prime is increasing in value, okay, because it's getting less negative, what that means is f double prime is greater than 0. And on the right side over here, f is increasing. Well, that means f prime is greater than 0. And on the other side of this, I can see I'm going from less positive to more positive. All those tangent lines are actually gaining value. So when I'm going from a less positive number to a more positive number for all those slopes, that's showing on this side f prime is also increasing on this side, which would actually mean the second derivative, or f double prime, also has to be greater than 0 because f is increasing. Therefore, the second derivative would be greater than 0. And I can see on this parabola, this is kind of looking at the difference between decreasing at an increasing rate and increasing at an increasing rate, okay? I'm concave up over there, the whole thing. And if you're like, whoa, what do you mean f prime is increasing? I'm saying the value of all these tangent lines are going from very negative to less negative. And if you don't think that's increasing, check your bank account. When you have a more negative number and that value in your bank account gets less negative, you're increasing in value in your bank account. So I'm going very negative to less negative to 0. That is actually an increasing value, all right? And it gets a little sketchy in here, no pun intended. So what we're going to do is we're going to look at the definition, okay? Definition, the graph of a differentiable function, y equals f of x is, okay? Concave up on any interval where the first derivative is increasing. So if f prime, I'm concave up. If f prime is increasing, and that by default means the second derivative will be greater than 0 or a positive value, okay? Or positive because it's greater than 0. And f is concave up, and f is concave down on any interval where my derivative is decreasing. My tangent lines are getting less and less, okay? That means f double prime is actually less than 0 or concave down or negative, okay? And that brings us into a concavity test, the second derivative test. And bottom line, we're going to do the second derivative test the exact same way we did the first derivative test, except we have to have the graph of a twice differentiable function, okay? And our second derivative test for concavity, we're going to use a number line test, except we're going to label it as a second derivative number line, so we know it's a number line test. And we're going to look for sign changes, okay? And if I have a sign change from positive to negative, hey, that's going to end up being a point of inflection for us here, okay? And because that's where my graph is going to change concavity. Something is concave up, a function is concave up on any interval where f double prime, the second derivative is greater than 0. The second derivative is greater than 0. That meant the function from which it came from was increasing. Concave down on any interval where f double prime is less than 0. Okay, that meant the function from which it came from was less than 0. And we're going to be talking about increasing at a decreasing rate, decreasing at an increasing rate, and all that good stuff. So you might want to run through this, try to make a little bit of sense out of it, all right? And we're going to be checking things out. Concave up, all right? Concave up. And I'm just going to try to draw a couple things here. So here's concave up. This is what's called concave up, right? So this side is concave up. And if I look on both sides, well, on the left side, if I'm thinking of this as f, this is my f function again, okay? The slope of these tangents would be f prime. Notice the left side, they are all negative. Okay, so that means the value of f prime is less than 0. But if I'm looking at the actual graph of f prime is increasing in value because I'm going from very negative to less negative. So that means it's increasing. And if it's increasing, that means the second derivative of that is going to be greater than 0, meaning concave up. And when I look at this side, well, I'm going from less positive to more positive, okay? F prime is still positive, but my function's derivative, these tangent lines are actually increasing. They're getting more in value as I go to the right, meaning concave up, okay? So let's just knock out a couple examples here before we call it the end of the day. And hopefully I can get a few things in. So what we're going to do is we're going to use the concavity test. Concavity test is the second derivative test, okay, to find concavity. Okay? And towards the end of this lesson, we're going to do a complete analysis on a whole function. Meaning, when's it increasing, when's it decreasing, when's it concave up, when's it concave down, where does it have a point of inflection, where does it have maximums and minimums, where are those places and points, all right? So we're just going to be looking here, we're going to say, hey, we know this is a cubic looking function, and hopefully you know, most likely, this thing could look a little something like this, where hopefully it's possible it could have a change in concavity, correct? And we're only going to be looking on the interval from 0 to 5. Okay, big deal. So, in order to find the concavity test, okay, we need to find the second derivative. Well, that's not going to be too rough. What's y prime? Well, the first derivative is 3x squared minus 12x. Okay, there we go. Now I need to find the second derivative. The second derivative is going to be 6x minus 12. Well, in order to find my critical points, and they're not really called critical points, okay? It's a second derivative test, but I'm kind of a simpleton here, and I think of these as critical, can't spell, critical second derivative points, because what critical second derivative points are, those are potential maximum, or they're potential points of inflection. And like I said, we're going to do this the exact same way that we did the first derivative test. So what I need to do is I need to find out when is f double prime of x equals 0. That's going to be a second derivative type critical point. And also, when does the second derivative actually does not exist, okay? And I'm going to look at all these. Well, over here when I'm looking on the does not exist side, well, I don't really have to worry about that because this is a polynomial function and it's differentiable everywhere as many times as you want. So this is not applicable on this side over here, but I can find out when does my derivative equal 0, my second derivative equal 0 on the other side. So that's just taking the second derivative and setting it equal to 0. Well, that would be when 6x equals 12. So when x equals 2 is a potential point of inflection. Then I would take that second derivative critical value, all of them, and I would place them into my second derivative test.
is my second derivative number line, and I'm going to put my positive 2 on there, and I know my second derivative equals 0 there, okay? So I do know, and it's important because I know when I plug 2 into the original function, I'm going to get something out. And also notice that critical second derivative point I found, hey, it's on the interval I'm talking about. And all I'm going to do is I'm going to take that second derivative, I'm going to take y double prime equaling 6x minus 12, and I'm going to pick a point on both sides of it. Well, if I took a 3, and again, all we're really looking here for is a sign change. Is it positive or negative? That's going to tell me concave up, concave down. Okay, so if I put a 3 in here, notice I'm going to have 18 minus 12, and so that's going to be what? That's going to be positive here, isn't it? So it should be concave up. And to be completely honest, I would probably typically take this and say minus 2. So then I'm always looking at when I plug it in, that's always a positive 6 times, what is this going to be when I put a 3 in there? Well, it's a positive value, therefore it's positive. When I test something over here on the other side, like say maybe, wait, I can't test 3's on this side, you bonehead. So I'm positive over here, right? This 3's on the right side. So Kruger, wow, you big fathead, you gotta make sure you're plugging in the right point here. So now I'm gonna test on the left side of 2. Well, that would be something smaller, like maybe 1. Well, if I put a 1 in there, I'm kind of zoning in on here and saying, hey, that's going to give me a positive 6 times, it's going to be a negative 1, meaning negative, so it's going to be concave down there. So if I needed to find out, because my second derivative is negative here, I have to be concave down here, and on this side I'm going to be concave up over here. So I was listing my intervals of concavity, and notice, I'm going to get rid of this guy a second. Notice I'm only listing them on this interval, okay? So I would actually put my second derivative line would be 0 here, and it would end out here at 5. I wouldn't put them all in there. That would be 5 because I'm only testing between there. So I would state my concavity to be where? Well, I'm concave down, and I'm concave up, where, you can call that CD and CU if you want, doesn't really matter. But here I'm negative from 0 to 2, so I'm negative, so then from 0 to 2 I'm concave down, which means, and then if they say, oh, justify your answer, I could justify that. That's because y double prime is less than 0. That's the justification they're looking for. And I'm concave up from 2 to 5. Justify your answer. Well, I can justify I'm concave up because the second derivative is greater than 0. All right? So we're going to zippity-doo-dah here to another example. Ooh, a trig function. Why a trig function? Because everybody loves trig functions. This is really very easy to picture, okay? Because if I really wanted to, I could come over here and I could say 1, 2, 3, 4. Here's my 2 pi. And if I was graphing a sine x, we know it just goes woo, 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 right? So here's my pi. I already know my intervals of concavity. But we need to calculus prove these. We want some justifications here. So what we're going to do is we're going to find the second derivative. Well, what's the first derivative? Well, what is the derivative of sine something? It's cosine something, and then it's really a chain rule times the x, which would be 1. So then the second derivative is what? What's the derivative of cosine? It's negative sine something times the chain rule, which is going to be a 1 again. So then from there, we need to find our critical points on that interval. So we're saying, hey, when does the negative sine x equal 0? Well, hopefully, you're picturing your unit circle, and you're like sine, okay? 0, pi, 2 pi, and so forth. Those are where I'm hitting my zeros. So I know
x is going to equal 0 at where? At 0, pi, and 2 pi. Well, check it out. These are endpoints anyways within my interval, but that doesn't matter. They're still critical points. Okay? So then I also need to kind of picture, this is when, I guess I should have backed up, get your mind organized. So this is when y double prime equals 0. And I also need to know, when does y double prime not exist? And again, because this is a trig function, they are smooth as silk. They're everywhere. This is not applicable here because the sine exists everywhere. It's a continuous wave with infinite numbers of maximums and minimums. And what I would do is, these are my critical second derivative points. So what I will do is I will take them over and I will make myself a critical second derivative line where my left is 0, my right is going to be 2 pi, and I have another critical value here of pi in the middle of it, right? So then what I got to do is I need to test this point out, okay? So I'm just thinking my second derivative is negative sine x. So I need to pick a point in here within the interval from 0 to pi. What would be a good one to pick? How about pi over 2? And what is the opposite sine pi over 2? Well, I always picture when I get these values, I get, oh, here's my pi over 2. It's 1, but it's the opposite of that. So this is actually negative 1, which means I'm concave down, right? And here at pi, I was 0. And here I was at 0. And here I was at 0. So what's a good number to pick between pi and 2 pi? I don't know, maybe right in the middle. How about 3 pi over 2? And remember, we're looking at our symbol, our unit circle. So if I'm testing between there and there, let's just test the vertical axis there. And when I'm doing that, I'm thinking negative sine 3 pi over 2. Well, what is the sine of 3 pi over 2? Well, that's the opposite of negative 1, isn't it? So this side would be positive, meaning it's concave up there. And that's all we're doing right now is we're checking concavity here. We've checked for maxes and mins increasing and decreasing. Now we're checking for concavity. And if I listed my concave up, concave down, when am I concave up? I'm concave up from pi to 2 pi, right? And I'm going to be concave down from 0 to pi. Those are my intervals of concavity, right? There they are. So what I'm going to do is I'm going to let you try to pick another one here. Okay, I'm going to throw this guy down to you. I'm going to have you work on this, and I'm going to be back, okay? Recommend you hit pause to try one. Give it a shot. Find my concavity. Using the concavity test, determine the intervals of concavity for this particular function. Notice this particular function is not on a particular interval. It's all real numbers. So one of the first things I would really want to identify is my domain. I don't have to write it all out. I know my domain, okay, is, oh, jeepers Christ. My domain is all real numbers x except 0. And when I'm looking at this thing, how do I know 0 is not out? Because that gives me undefined down there. And I know at, in my head, x equals 0, I have a vertical asymptote, not a hole, because if I plug that 0 in there, I get negative 2 over 0, which is a vertical asymptote. So why don't you go through, find your second derivative points, okay, and then give me the intervals of concavity that you come up with. All right, so I'm back here. So hopefully you found your first derivative. If you're like, oh crap, it's a quotient, you're right. Don't worry about it. It's the derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared, which gives me x squared minus 2x squared plus 4x, right, over x to the fourth, which really is negative x squared plus 4x over x to the fourth. Well, I can look at this and I can reduce and say that's negative x plus 4 over x to the third. That's my first derivative. Well, I need the second derivative. So I got to dig in a little deeper. So because that's the second derivative, or the first, the second derivative is, again, the derivative of the top times the bottom minus the derivative of the bottom times the top, all over the bottom squared, which is going to give me what? Negative x cubed. And then this is, I always take that and tag that with him, so that's really negative 3x squared times negative x. That gives me plus 3x cubed, and then that's minus 12x squared over what? X to the sixth, which gives me what? 2x to the third minus 12x squared over x to the sixth, which is going to make me look at that. I'm going to take this guy and I'm going to wrap him over here. And I'm going to say, hey, that equals, I can see I can factor. What I'm going to do is I'm going to take a 2x squared out of everybody in top. That gives me an x minus 6 over x to the sixth, which means 2 times x minus 6 over x to the fourth is my second derivative. Okay? Now that I have the second derivative, now I got to look for those second derivative critical points so I can find concavity. So I got to say, okay, when does y double prime actually equal 0? Well, because it's a fraction, it's the only factor in the numerator that can actually equal 0. So wouldn't that be when x minus 6 equals 0? So I should have a second derivative critical value at 6. And also, when does y double prime not exist? Well, I know it doesn't exist when x to the fourth equals 0 or when x equals 0. Now, remember, is it possible to be a point of inflection at 0? And the answer to that is going to obviously be no, because 0 is not defined in the original function. But it's still a critical value for me to check on my number line test. So from there, I'm going to do my y double prime line, and I'm going to put 0. I know I'm undefined there, and I know out here at 6, I'm 0, and this side is negative infinity. This side is really infinity. So now what I'm doing is I want to take this second derivative I have, which is a positive x minus 6, and then x to the fourth. And what I really want to do when I'm testing these, okay, picture it, the denominator, no matter what value of x I put in, because it's an even power, the denominator is always going to be positive, and this 2 is always going to be positive, right? So what's going to happen is what value for x I put in there is going to control whether the top is positive or negative. Well, if I came back here and I put a negative 1 in there, okay, what's that going to give me? Well, that's going to give me a negative 7, so it's negative. So that should mean I'm concave down there, right? And when I put in between 0 and 6, well, pick anything, like maybe 5, any number between, but not 0 or 6. If I put a 5 in there, well, now it's 2 times negative 1. It's still negative, meaning still concave down. But now when I pick anything bigger than 6, like 7, notice denominator stayed positive, but now my numerator is 7 minus 6, so now it's positive 1 times 2. Now that's a positive number, so I am now going to be concave up. And what I'm going to do, and it's really important for this second derivative test, because we're going to look at this graph here in a minute, and we're going to say, whoa, I've never seen that change in concavity there. But I can see this is concave up. When am I concave up? I am concave up from 6 till infinity. Okay? And that's going to mean things for me because that means, well, I'll get into that in the next lesson. And when am I concave down? Well, when am I concave down? I'm concave down from negative infinity all the way up to 0, union with 0 to 6 is where I'm concave down. Okay, so I can find these intervals of concavity. And actually, I'm going to leave it up to you. Okay, I would encourage you to look at this, go back and look at, I'm going to throw it in there. We're going to graph this guy really quick. Whoa, stop freaking out. We're going to get a control divide. Whoa, come on, baby. Give me this in here. We're going to go control divide. We're going to put that fancy fraction of x minus 2 in there. And we're, and we're going to get an x squared downstairs. And I got to come up here, and I need my x there yet. And I'm going to graph that. And there it is. Okay. Well, factor fiction. Pretty tough to see that there is going to be a point of inflection over here at the number 6. But I did, 1, 2, 3, 4, 5, 6. But I did have a change in concavity, all right? So we could zoom in on this graph a little bit. I don't know, how much do we want to zoom in? Let's say I don't have to go up because I do have a horizontal asymptote there, but let's say I go to 3 here, and it really doesn't show me. Come on, baby. Let's say maybe -3. That doesn't really give me anything, but when I say menu, analyze the graph, and I'm looking for a point of inflection, well, I should have one somewhere around 6, right? There it is. I do actually, and it's really difficult to see, I actually do have a change in concavity here because on the right side over here, I'm concave up, and over here I'm concave down. Okay? And it's important because sometimes it's really hard to see in the graph. But we look at the graph, we analyze the function using our derivative tests, and it tells us what is going on. Notice there was not a point of inflection at 0. Okay? So, takes me down to my last slide that I'm going to talk about here. And then I just have a couple tidbits for you on that. But definition, a point of inflection. A point of inflection is a point on where f, a point on f where the graph of a function has a tangent line and where the concavity changes is called a point of inflection. Okay? So just think about this, points of inflection. Mainly, it's going to have you're going to have a tangent line there, and you're going to have a change in concavity. Points of inflection is where you are increasing or decreasing at the greatest rate of an application problem. But find points of inflection, okay? And we're going to do that using the second derivative test, by taking f double prime when it equals 0 and when f double prime does not exist. These are going to be my critical values of the second derivative. Now, when you're on the AP test and they're talking about quote-unquote critical values, please understand those are first derivatives they're talking about. So these second derivatives really aren't critical points. They're important points of the second derivative to find a point in concavity or a change in concavity. Okay. Also, once we do that, it's the same process as the first derivative test. We're going to do the same process. It's just using the second derivative. Okay? Simple as that. And if f double prime of x equals 0, and change of signs. Okay, what happens? Point of inflection at that x equals c value, or right here. Okay, and also look down the road. We investigated this early. The point of inflection. So at a point of inflection, remember that meant f prime of x has a max or a min at that point. Remember? Okay, because we're just look back when we were analyzing just the graphs, okay? And a point of inflection when f prime has a max and min, okay? So remember, second derivative, a point of inflection is when it changes sign. Okay, that's where my function changes concave up, concave down. So I have a change in sign there, meaning change in concavity. But the graph of the first derivative, if I was comparing f to f prime to f double prime, a point of inflection on f is a max or a min on f prime, and it's a x-intercept on y double prime, okay? And that's about where I'm going to cut her off for today, and tomorrow we're going to start out on here. So I don't know if you want to copy that portion onto your note sheet on the next one. If not, don't worry about it. And we'll be back tomorrow. Good afternoon. Where is it? There it is.